Alright, I want to go through one good example of finding absolute max and absolute min. Of a function like this over a closed region. So since this is happening over some triangle out there and you have a nice smooth continuous surface, there's got to be a maximum and minimum that happens somewhere. That's guaranteed with a nice differentiable surface like that. Got to be somewhere on this region. Could be at the corners, could be along the boundaries, or it could be in the interior if there's a horizontal tangent plane at some point inside, if there's a critical point inside the region. So we got to see what that is. A lot of the work happens with this picture over here, and then we got to think about our partial derivatives over there for the critical point part. This is given the vertices, so I just want to make the picture so I can follow what's happening. But this is a nice simple triangle out here we're interested in. And so think about what each of these lines are. That's the line y equals 0 for those certain x values. This is the line x equals 0. And the diagonal there, that would be y equals 3 minus x. Diagonal line, so you can write it down as a function, as a relationship between x and y, and we can do some substituting there. So all of those I should be able to make them into Calc 1 problems, right? Make them into one variable situations because they can all be written as one variable functions. So for the red one, f of x comma 0, if the y value is 0, what I get from substituting the 0 in there is just the minus x term and the plus 4. And so the derivative of that is just negative 1. That's always decreasing as x goes along. So that's going down as I go across here. So maybe this corner is a max, maybe this corner is a min. There's no max or min between them along that boundary because this is never equal to 0. Not this. The derivative's never equal to 0 there, so there isn't any max or mins along there. I only have to worry about the corners on that side. Go to the black side, do the same thing. Well, the black side's going to be more complicated because y is 3 minus x. So I'm looking at f of x 3 minus x. I'm substituting 3 minus x for y in this. So I got 2x 3 minus x minus 3 minus x plus 4. Remove some parentheses and see what we got here. Combine some like terms. Regular descending order, that's 5, 6. Okay, I got 2x, negative 2x squared plus 6x plus 1. Now, I want to see if there's any minimums along that piece. This is a function of one variable. Now, some kind of curve along here, well, it's actually a downward parabola somewhere. So let's find out if there's any max or mins on that. The derivative of this, I keep writing it out because I'm confused about which symbol this would be, right? It's a one variable function now, so it's the derivative of this thing just with respect to x, of course, but it's kind of a partial, but it's kind of a single thing now, so I just wrote it out. Derivative is negative 4x plus 6, so that's equal to 0 when 6 is 4x, so x equals 3 over 2. That happens to be within the x values of our region right there. Not inside the triangle, but the x values have to go from 0 to 3 for this. This is right halfway in between there. There's a point out there. On the line, so if x is 3 halves, y is 3 minus 3 halves. So we're looking at an ordered pair, 3 halves, 3 halves. That's on the boundary. And then the corners, of course, could be, well, I know this is a downward parabola, so maybe these are mins. I don't know, we'll see. The corners, possibilities there. One more piece to do. Before I even get to partial derivative part, one more one variable piece to do. What is f of 0 comma y when x equals 0? Substitute 0 in for x. and you get 0, 0, negative y plus 4. Derivative is negative 1. So it's never equal to 0. There's no max or min value along that boundary. That's going down as y goes up. So this is higher. If you picture the surface here, it's kind of going downward along this line and along this line. But then there's this downward parabola over here. So this might be a max, I'm thinking. And these corners might be mins, and this might be a local max out here. We'll see. We'll see. I'm thinking maybe this is max and these are mins, because I know not just where it's equal to 0, but I know kind of the shape of this thing, right? It's down. This is like a vertex of a parabola up here. So those might be mins. This might be a max. And these are sloping downward, so I might have a max over at this corner, local at least. But I want to see what the absolute max is, so I got to do f of all of those points anyway. The other thing I need to know is the actual partial derivative piece. Anything in the inside there could only be a min or a max if both partials are equal to 0. So fx and fy, my partial derivatives. Derivative with respect to x is 2y minus 1. Derivative with respect to y is 2x minus 1. Could both of those be equal to 0 at the same time? Well, in this case, pretty easy. Algebra situation. That happens when they're both equal to 1/2, which is out in the middle of my region out here. I've got a potential point right there. I don't know enough of the shape about this thing to speculate as to what that is, but that's one more ordered pair that's on my list of possibilities. So my table for this thing now, I got corners here, 0, 0, 0, 3, 1/2, 1/2, 3/2, 3/2 was the point from the diagonal boundary, and then over here at 3, 0, there they are. Doesn't matter what order I put them in. I'm going to evaluate f of x, y at both of these things. And I could also get what this d thing is. That only applies to the interior ones. That doesn't tell me anything on the boundaries, but that tells me something about the ones on the interior, which is just this one here. I'd like to know the d at this point, know if it's a saddle point or what out there in the middle. So let me think about that first for a minute. I need my second partials. Put those in kind of a little matrix and do the determinant thing if you want to think about it that it's this times that minus this one squared, or fxx. Of course, that's the derivative of this with respect to x. The derivative of this with respect to y is 2. The derivative of this with respect to y is also 0. So my little determinant thing would be 0 times 0 minus 2 times 2, or negative 4. So the derivative, the d thing is negative 4 there. So that's a saddle point. If it comes out less than 0, it's a saddle and not a max or a min. So it's not going to be an absolute max or min either. Plug the actual things into my function, and I get 4. If x is 0 and y is 3, get positive 1. I'm doing this quickly, but I think I'm doing it right. If I put in a half and a half, I get half minus a half minus a half plus 4. I think that was 7 over 2. This point that I thought maybe was my vertex max out there, let's see what happens there. That's 2, 9 over 2, minus 3/2 minus 3/2, 3 over 2 plus, I think I got 11 over 2 there. And 3, 0. If x is 3 and y is 0, I get 1 again. There's kind of some symmetry around x equals y in this. If you switched x and y, you get exactly the same function back. So there's some symmetry there, and so these aren't surprising that those matched up. But we're just looking at the winner and the loser on this thing. What is the highest overall value? And it ends up being at the origin there. And the lowest overall value is a tie between these points. That's my absolute min is 1 at those 2 points. And the absolute max is, wait, this is higher than 4. I'm sorry, I circled the wrong thing. 11 over 2 is bigger than 4. Absolute max is 5.5 out there at that sort of the vertex along that diagonal boundary. So the absolute max is here at 3 halves, 3 halves. And the absolute min is 1 at these 2 corners. It can easily be a tie between some different points out there, and that's not surprising. Alright, so that's the full treatment of these things when you're dealing with the interior and you're dealing with the boundary on a closed region.